Hello and welcome back. In a previous video, we studied the relationship between pressure and depth, and we found that it was the weight of the water itself that causes pressure to increase with depth. Now at this point, I want to look at whether other types of external forces can affect the pressure of a fluid. And to understand the relationship between an external force and the change in the pressure, I want to look at the simple example of an incompressible fluid. So over here on the right, I have a picture showing a container which is holding an incompressible fluid. And floating on top of this fluid is a plunger which can move up or down. So the idea is that if I apply a force pushing downwards on this plunger, the water has to exert an equal and opposite force pushing upwards. Otherwise the plunger would move, compressing the liquid. So by setting these two forces equal to each other, we can find the change in the pressure. So the applied force must be equal to the change in the pressure of the fluid times the area of the plunger. So the change in the pressure is going to be equal to the applied force divided by the area over which the force is being exerted. And so it turns out that we can actually use this simple relationship between the external force that's applied to a fluid and the change in the pressure of the fluid to gain mechanical advantage. And these types of machines are called hydraulics. And the basic idea behind the hydraulic machine is that you take two containers like the ones that I had shown in the previous slide, where there's this movable plunger placed on top of an incompressible fluid. And you connect these two containers together with a hose so that the fluid from one of the containers can flow into the other container. So the idea is that when I apply a force F1 to a plunger which has an area A1, the pressure in the fluid just beneath the plunger increases by an amount that's equal to F1 divided by A1. Now because these two containers are connected together by a hose, it means that the pressure that's just below the other plunger is going to increase by the same amount. And this means that the force that's being pushed upwards by this fluid is going to increase, and the amount that the force increases by is equal to the change in the pressure that's beneath the plunger times the area of the second plunger. And since the change in the pressure is equal to F1 over A1, we see that the force that is exerted upwards on the second plunger is equal to the force that we exert upwards on the first plunger times the ratio of these two areas. And so the basic idea behind this is that, for example, in this picture, because the area of the plunger on the right is so large, that when the pressure changes, because the pressure is being exerted over such a large area, the force that is exerted upwards on the second plunger is very large. And conversely, because this plunger over here is very small, the force that is exerted upwards by the pressure of the fluid on this plunger is relatively small. So the force that I have to exert downwards to keep the plunger there is also going to be relatively small. So what we can do with this is we can actually magnify forces. By having plungers of different sizes, I can actually increase the force that comes out of this. So over here I could apply a relatively small force to this input side, and then on the output side I'd get a very large force. Now it's important to understand that even though hydraulics allow you to magnify the force that you're applying, hydraulics don't give you something for nothing. In other words, the work that you do in pushing the input plunger is going to be equal to the work that is done by the output plunger. Now remember that work is equal to force times displacement. So in the previous slide we already found how the forces of the two plungers are related. Now we need to see how the displacements of the two plungers are related so that we can show that the work that we do on the input plunger will be equal to the work that we do on the output plunger. And the basic idea behind this is that because the fluid is assumed to be incompressible, when I push down on the input plunger and I displace some of this fluid, the input plunger has to go upwards, and the volume that is created by the input plunger moving upwards is equal to the volume of the fluid that I displace when I push down on the input plunger. So by setting these two volumes equal to each other, so if I set the volume of the fluid that's displaced by moving the input plunger down equal to the volume that's created by the the output plunger moving upwards, well, these volumes are equal to the area of the plunger times the distance over which the plunger moves. So here this is the area of the input plunger times the distance that the input plunger moves is equal to the area of the output plunger times the distance that the output plunger moves. So I see that the distance that the output plunger moves is equal to the distance that the input plunger moves times the area of the input plunger divided by the area of the output plunger. So now if I calculate the work that is done by the output plunger moving upwards. This is equal to the force that is exerted on the output plunger times the distance that the output plunger moves. Now remember that the force that is exerted on the output plunger is equal to the force exerted on the input plunger times the area of the output plunger over the area of the input plunger. And the distance that the output plunger moves is equal to the distance that the input plunger moves times the area of the input plunger divided by the area of the output plunger. Now if we look at this, we can see that these two ratios are going to cancel out. And so we see the work that is done by the output plunger is equal to the force that we exert on the input plunger times the distance that the input plunger moves. So this means that the work that we get out of the output plunger is just equal to the work that is put into the input plunger. So in fact, as I said before, you don't get something for nothing. The work that you put into this is going to be equal to the work that comes out. So when you decrease the force that you have to apply, it turns out that you increase the distance over which you have to apply the force. And you increase that distance in just the right way to conserve energy. So let's go ahead and look at an example. In this first example, we have a hydraulic machine, but the plunger on the left has an area of 15 square centimeters, and attached to this plunger is an ideal spring, which has a spring constant of 1600 newtons per meter, with the other end of the spring attached to a fixed wall. And the idea is that when I don't have any blocks sitting on this plunger over here, the spring is initially uncompressed. Now the question is, when I place a 40 kilogram block on this plunger over here, which has an area of 65 square centimeters, how far does this spring over here get compressed? So the basic idea behind this problem is that when I place a 40 kilogram block on top of this plunger, it'll increase the pressure of the fluid. And as a result, the pressure underneath this plunger is going to increase, causing an upward force. And that upward force is going to move this plunger upwards, compressing the spring. And the plunger will continue to move upwards and compress the spring until the spring force that's pushing down on the plunger cancels the upward force that's caused by the pressure of the fluid. So in other words, we have the force that's exerted by the spring needs to be equal to the force it's caused by the pressure. So that's equal to the change in the pressure times the area of this plunger. That's A1. And the change in the pressure is equal to the force that was exerted on plunger 2 divided by the area of plunger 2. And the force that's exerted on plunger 2, remember this is the force that's caused by the weight of the rock. So this is equal to the mass of the rock times g divided by the area of plunger 2. Now the last thing we need to do is we're trying to figure out how far the spring gets compressed. So remember, the spring force is equal to the spring constant times the distance that the spring gets compressed. So solving for delta x, we see that delta x is going to be equal to the weight of the rock divided by the spring constant times the ratio of the two areas. And if we plug all these numbers into a calculator, we'll see that the spring is going to be compressed by 5.7 times 10 to the minus 2 meters, or 5.7 centimeters. Now let's go ahead and look at one more example. In this example, it says a hydraulic lift uses oil which has a density of 800 kilograms per cubic meter. The input piston for the lift, that's supposed to say lift, is located 1.1 meters above the output piston. So over here is the output piston, which is holding a car, and the input piston is up here, 1.1 meters above the output piston. The radius of the input piston is 0.012 meters, and the radius of the output piston is 0.15 meters. The question asks, how much force do we need to apply on this input piston in order to lift a car which has a weight of 2,500 newtons? And so to answer this question, I'm going to need a little bit of space, so let me go ahead and open up OneNote. Now I've gone ahead and I've drawn another picture of this problem, and an important thing to understand about this problem is that because this output plunger is below the input plunger, the pressure at the output plunger will be greater than the pressure at the input plunger, and the difference between these two pressures is related by rho GH. So in other words, we know that the pressure at the output plunger is equal to the pressure at the input plunger plus rho GH. Now the pressure that's exerted on the output plunger has to be equal to the force that we have to apply to this plunger to cause the car to go up, divided by the area of the plunger. So we have the pressure on the output plunger has to be equal to the force that we have to apply on the output plunger divided by the area of this output plunger. And because we're going to assume that this output plunger is a circle, the area is just equal to pi times r out squared. And this has to equal the force that we apply to the input plunger divided by pi r in squared plus rho gh. So now all we have to do is solve for the force that we apply to the input plunger. So to do this, I'm going to subtract rho gh to the other side. So I have that the force that we apply to the input plunger divided by pi r in squared is equal to the force that we apply on the output plunger divided by pi r out squared minus rho gh. And finally, if I multiply off this pi r in squared, I see that the force that we exert on the input plunger is going to be equal to the force that we exert on the output plunger times pi r in squared divided by pi r out squared minus rho gh times pi r in squared. And now if I just plug all this into a calculator, I see that the force that we have to apply to the input plunger is only 127 newtons. So we can see in this example how if you have plungers that have vastly different areas, you can really magnify a force very significantly. So for example in here, we can see that the radiuses are approximately a factor of 10 different, which means that the area of this output plunger is 100 times larger. So we only have to apply a force that's, less than 100 times the force that we get out of the output plunger. So at this point, I think I'd like to end this video, and in the next video, I'm going to talk about something called the continuity equation, which is basically the equation that explains why when you do something like hold your thumb over the end of a hose, why the water sprays out at a higher speed.